lecture series on complex analysis for undergraduate students. Today's lecture is evaluation of real improper integrals. We are continuing with the evaluation of real improper integrals. We are learning, that is, how the residue theory can be used to evaluate real integrals. We had seen that the residue theory can be applied to evaluate the improper integrals of the form of minus infinity to plus infinity f x cos s x dx are of the form minus infinity to plus infinity f x sin s x dx. Certainly, here we had assumed in the last lectures that f x is a rational function, that is, it is of the form p x upon q x, where both p and q are the polynomials, and we had assumed that q does not have any real 0. Moreover, we had assumed that the degree of the q, that is the denominator, must be at least 2 degrees higher than the degree of the numerator polynomial p. We were requiring that degree condition to show that the integral of your e to the power this f z e to the power I s z d z goes to 0 on a semicircle S as limit r as r is approaching to infinity. Now, assume that this f x is having all the conditions as such, that is, my denominator does not have a real 0, and moreover this p x and q x, they are polynomials, it is a rational function, none of them have a common factor, and but the only condition is that this p x and q x, they are not satisfying this degree condition, that is, the difference between the degree of denominator and numerator is not at least 2. Now, suppose here if the difference is 1, then we are going to face the problem in showing this limit as r is approaching to infinity, showing that integral s f z into e to the power minus s z d z goes to 0. For that, sometimes we require one particular kind of inequality which helps us in showing this convergence, that is called Jordan's inequality. What is this? This is actually integral 0 to pi by 2 e to the power minus r sin theta d theta is less than pi upon 2 r for r positive. What we are having is that the integral of e to the power minus r sin theta with respect to theta on the range 0 to pi by 2, this is bounded by pi upon 2 r when r is positive. To understand that what is this inequality and how we are going to use it in our evaluation of integral, let us first understand this one, or rather first we would show that this is true. For showing that this is true, we would like to compare two functions, one is r sin theta, another is theta upon 2 pi. So, if we see sin theta, the curve for sin theta between 0 to pi by 2, this is the curve for sin theta, and the curve for y is equal to 2 theta upon pi, this is the curve for y is equal to 2 theta upon pi from 0 to pi by 2. Now, we see from here that for complete range from 0 to pi by 2, this function 2 theta upon pi, this is lying below than this curve sin theta. What we are concluding from here? We are concluding that sin theta would always be greater than or equal to 2 theta upon pi in the range 0 to pi by 2, because at 0 both of them are equal. Now, we will use this to show or to prove this Jordan's inequality. We want to prove 0 to pi by 2 e to the power minus r sin theta d theta is less than pi upon 2 r for r positive. We have just shown that r sin theta that sin theta is greater than 2 theta upon pi. So, we would use that sin theta is greater than 2 theta upon pi. So, we would write e to the power minus r sin theta. It would be actually 1 upon e to the power r sin theta. Since sin theta is greater than 2 theta upon pi, r sin theta would be greater than 2r 2 theta upon 2r theta upon pi, and that would be in the denominator. So, what we would get actually e to the power minus r sin theta is less than or equal to e to the power minus 2 r theta upon pi in the range 0 to pi by 2. We are interested only in the range 0 to pi by 2 because this integral is on the range 0 to pi by 2. If this is happening, that says is that this integrand is bounded by this function for all the for whole the range. What it says is that from here that integral 0 to pi by 2 e to the power minus r sin theta d theta, this would be less than or equal to integral 0 to pi e to the power minus 2 r theta upon pi d theta. Now, integrate this function, this is more simple function, this is just exponential function. Its integration would be minus 1 upon minus pi upon 2 r e to the power minus 2 r theta. So, minus pi upon 2 r e to the power minus 2 r theta upon pi. Evaluate it from 0 to pi by 2. Evaluation from 0 to pi by 2 at 0, because it is a minus sign. So, first let us say have evaluation at 0. At 0, this theta is equal to 0, this would give me 1. At theta is equal to pi by 2, this would give me e to the power minus r. So, what I would get it as minus pi upon 2 r 1 minus e to the power minus r, this minus sign will not be here. So, what it says is this is pi upon r 1 minus e to the power minus r, whatever be this 1 upon e to the power minus r, that is a number which is smaller than 1. So, what we would be getting that this number would be always smaller than, that is you are subtracting, that is you do have some positive number minus some positive number. So, certainly it would be less than pi upon 2 r. So, we had shown this Jordan's inequality, that integral 0 to pi by 2 e to the power minus r sin theta d theta is less than pi by r. Let us see that is how we are going to use this in evaluation of the integral, where my f x is failing our degree condition. So, for that let us see one example. Evaluate the integral minus infinity to plus infinity x sin x upon x square plus 2 x plus 2 dx. Let us see this integral. This integral is of the form x upon x square plus 2 x plus 2. This is my f x into sin x. So, we are having is f x sin x dx kind of integral. Moreover, here my function f x, if I see, it is x upon x square plus 2 x plus 2. So, it is again of the form of the polynomial. So, what let us try to solve it. We are having our f x as x upon x square plus 2 x plus 2. We do have that p x would be x and q x would be x square plus 2 x plus 2. P x is equal to x is a polynomial, q x is equal to x square plus 2 x plus 2, this is also a polynomial. If I find out its roots or its zeros, there would be actually x plus 1 plus I and x plus 1 minus I, those would be the factors of this denominator. So, I would not get the real zeros for this one. What it says is that I am having all these conditions satisfied, that is it is a rational function, both are polynomials, the denominator does not have a real 0, but the condition, one more condition about the degree. Degree of p x is 1, p x is equal to x, the degree of x is 1 and degree of q x is 2. So, the difference is only 1, it is not greater than or equal to 2. So, that condition is not being satisfied. Let us see. Go ahead with the as usual method, that evaluation of integral of minus infinity to plus infinity x, f x sin x dx. So, for that we always used to define the corresponding complex function as f x e to the power I z. So, here we would take the f x, so f z, z upon z square plus 2 z plus 2 into e to the power I z. So, this we would take our corresponding complex function. Let us make this factors over here. So, we get z e to the power I z upon z plus 1 plus I upon z plus 1 minus I. That says is that the zeros of denominator q z are your minus 1 minus I and minus 1 plus I, both are complex numbers, and they are your minus 1 plus I, this would be lying in the upper half plane, and minus 1 minus I, this would be lying on the lower half plane. So, we do have one pole or one isolated singularity in the upper half plane, and that is also a simple pole, and z is equal to this qz pz is not 0 at that z naught point. So, it says is that we would go with our usual method. Let us start it. That says is that I would like to use our residue method, which said is that is if the function is fz fx e to the power fz dz using the, and which has a number of finite poles in on a simple closed inside a simple closed contour, we could go ahead with that. The integral value would be the sum of the residues at 2 pi I times sum of the residues at those simple poles. So, let us try to apply it. Let us see. This is what is my curve which I am taking, for which I would like to change my integral on this closed contour. The closed contour which I would be taking is consisting of the point your this S and from minus r to plus r on the real line. So, we are taking this semicircle bounded by the real line from minus r to plus r. My pole in the upper half plane is only this minus 1 plus I, this is your plane, this is your isolated singularity, this is only in the upper half plane. We want so, by residue theorem we do have that integral along this one should be equal to the 2 pi I times residue at this one. So, let us see what is my function. My function is z e to the power I z upon z plus 1 plus I into z plus 1 minus I. First, we are going to calculate the residue at the pole minus 1 plus I. We would use our first definition or first method of calculation of residue, which says is the residue of a function f z at z is equal to z naught when z naught is a simple pole is limit as z is approaching to z naught, z minus z naught f z. So, here your z naught is minus 1 plus I. So, we are using this definition, residue at z is equal to minus 1 plus I of f z would be limit as z is approaching to minus 1 plus I into z plus 1 minus I into f z. Now, if I am multiplying my f z with z plus 1 minus I, we see here that in the denominator we are having z plus 1 plus I and z plus 1 minus I. So, what I would get actually, I would get limit z is approaching to minus 1 plus I, z e to the power I z upon z plus 1 plus I. So, this limit says is just evaluate it at z is equal to minus 1 plus I. If I am evaluating it at this one, z would be minus 1 plus I e to the power I into minus 1 plus I, that would give me minus 1 minus I, and z plus 1 would be I. So, the denominator I would get 2 I. So, I am getting it minus 1 plus I into e to the power minus I minus 1 upon 2 I. So, using our residue theorem, what I do get, integral along this closed contour C. Closed contour C consists of the semicircle S and the real line from minus r to plus r. So, this closed contour we are having is, we can subdivide it into integral from S on the semicircle S of the function z e to the power I z upon z square plus 2 z plus 2 and plus integral from minus r to plus r of the function f z. Now, minus r to plus r, this is a real line, this is only the real one. So, I could make this parameterization and we could say this is x e to the power I x, x square plus 2 x plus 2, that is z is equal to x, the parameterization we are taking. Now, this integral by residue theorem should be equal to 2 pi I residue at z is equal to minus 1 plus I of the function z e to the power I z upon z square plus 2 z upon 2. Residue just now we had calculated as minus 1 plus I e to the power minus I plus 1 upon 2 I, multiply it with the 2 pi I. So, 2 I would get cancel it out, I would get it minus 1 plus I times pi into e to the power minus I plus 1. Now, the thing which is remaining is just to show that this integral of z e to the power I z upon z square plus 2 along the semicircle S, this approaches to 0. As r approaches to infinity, then the second integral minus r to plus r x e to the power I x upon x square plus 2 x plus 2, this will approach to the integral minus infinity to plus infinity, or it will actually give the Cauchy principal value, and then we could find it out this integral. So, let us try to see this integral on a semicircle of this function f z. We want to prove that as r approaches to infinity, this integral of z e to the power I z upon z square plus 2 z plus 2 d z on the semicircle S approaches to 0. See, if I do take this function z e to the power I z upon z square plus 2 z plus 2, we could write it as mod of z into e to the power mod of e to the power I z upon z square plus 2 z plus 2 absolute value of this. Or this again we could write it as the lower one z square plus 2 z plus I, we could say that is it is z plus 1 plus I and z plus 1 minus I kind of thing, and from there you see we could get it here. Let us see, your mod z is here, from here if I take this mod z common, I would get mod z whole square outside and then 1 minus root 2 upon z. When mod z is greater than r, root 2 upon mod z, that would be less than 1. That says is 1 minus this thing, this would be a fixed constant, this is a smaller constant, and mod z is getting cancelled out over here, and here I would be getting only mod z. Since mod z is greater than r, 1 upon mod z would be less than 1 upon r, and what is remaining e to the power I z, we do know the absolute value of e to the power I z is 1. So, what thing remaining is a constant upon r. So, we have got that this is bounded by k upon r when your z is greater than r. But this is let us see, that is denominator how we have got it out. This is the explanation for this. Z square plus 2 z plus 2 is equal we could write as z plus 1 plus I into z plus 1 minus I. So, I am writing that absolute value of or the mod of x into y as mod of x into mod of y. Now, here I would be using is that z plus 1 plus I would take z as x and this 1 plus I as the y, then we do know mod of x plus y, we could write it out as this is greater than or equal to a mod of x minus mod of y. So, by that we would be getting it as mod of z minus mod of 1 plus I, then mod of z minus mod of 1 minus I. Mod of 1 plus I we do know is square root 2, mod of 1 minus I is also square root 2. Thus, we have got that this would be larger than or equal to absolute value of z minus square root 2 whole square. This is what we have written over here. So, thus we have got it what we have got now. So, from here if I use the ML inequality on this integral, this function is bounded by k by r and this is on this semicircle with the radius r. So, here using this ML inequality we could say this integral absolute value of this integral would be less than or equal to m, that is the bound, that is k upon r, into the length of the arc. Length of arc here would be pi into r. So, what we are getting is this is bounded by a constant. Now, this constant is independent of r. So, now if I put limit as r is approaching to infinity, this constant is not going to change. So, what we have got, we do not know how could we say that this is, because till now how we had shown it, we had shown that is whatever this bound was coming, that was depending on r, and thus we are saying is as r is approaching to infinity, that bound is becoming smaller and smaller, and since it is a positive quantity, so that has to be equal to 0. But here we are not able to find out the bound, that it is also decreasing as r is increasing. So, that we cannot do. Does it says is that this integral does not approaches to 0? No, it is not. The only thing is that we had used this method, that is the bound which we had find it out. This is a little bit more upper bound. It may happen that we may find out some more nice bound which is depending on r and which is approaching to 0. Can we use? Yeah, here comes, that is how we are going to use the Jordan's inequality. Let us see. Again write this function z e to the power I z upon z square plus 2 z plus 2. This again we would be writing is absolute value of mod z into mod of e to the power I z upon mod of z minus root 2 whole square. This is what we had already obtained. Now, we want this integral on this semicircle S. On this semicircle S, we can use this parametric representation. Then on this S z I could write as r into e to the power I theta for this fixed r, and theta is ranging from 0 to pi. This is the parametric representation of my semicircle. Now, that says this we want this bound on this semicircle only. So, let us see on the semicircle, if I write it out, what my function will happen. E to the power I z on this semicircle, if I try to find out its bound, z I am replacing as r e to the power I theta. Now, e to the power I theta by Euler's formula, I would be writing it as cos theta plus I sin theta. That says I would get e to the power I r cos theta plus I sin theta. Now, let us see. Here I would get e to the power I r cos theta, and here I would get e to the power minus r sin theta. So, what we are getting is absolute value of e to the power I r cos theta into absolute value of e to the power minus r sin theta. Now, absolute value of e to the power I r cos theta, whatever be this e to the power I x, this modulus is always 1, because it is cos x. By the Euler's formula, it is cos x plus I sin x, and it so sin square x and cos square x plus cos square x is always 1. So, whatever be this I times this one. So, this is 1, and r we are taking as a positive value. Sin theta we are saying is theta is lying between 0 to pi. We do know in the upper half, that is from 0 to pi, sin theta is always positive. So, we are getting is that this quantity is positive, this would be some quantity, and e to the power any quantity, that is always going to be the positive. So, the absolute value would be e to the power minus r theta. Now, write this function f z as now r z I am representing in this parametric presentation. So, I would get the integral s on s f z dz as integral from 0 to pi your f r I theta, and your dz would be getting from here I r times e to the power I theta d theta. So, that we are going to do it. So, let us see f z, this is this one. So, I am writing it as f r e to the power I theta. From here, if I do write, I would be getting this mod z e to the power I z upon z minus square root 2 whole square. This we could say is, because the first term we had already shown, here what I would get it r e to the power I theta, mod of r e to the power I theta, that would be simply r, and here I would be getting is mod of, or rather you could say is that is in the beforehand we had obtained that this whole quantity was less than k by r. So, let us use it from there, that is k by r, and e to the power I z is equal to mod of e to the power I z is equal to e to the power minus r sin theta. So, now you see we had obtained a modified or finer bound for our f z. Previously, I had find out the bound for f z, that was k by r only. Now, I had find out my bound for f z as k upon r e to the power minus r sin theta, where my theta is actually on this parametric representation of the semicircle S, my z can be written as r e to the power I theta. So, we have got this a finer bound. Let us use this finer bound. So, now we are writing my integral S f z d z. If I just represent it in the parametric form, we could write it as a line integral 0 to pi f of r into e to the power I theta into your if you do remember, that is if z is equal to your some z t, then you are writing it as f t, f of z of t, and then z dash t dt. So, that is what we are writing here, z dash theta d theta. So, it is I r e to the power I theta d theta. Now, use this ML inequality now. So, we have got f r e I to the power theta is less than or the bound as k upon r e to the power minus r sin theta, and the integral S f z d z. Now, on this one we could write as integral of 0 to pi f r e I to the power theta e I theta d theta, and this r is constant with respect to theta. So, I can take this I and r outside. Now, take this absolute value, this I could say is this is x and this is y. So, it would be mod of x, absolute value of x into absolute value of y. Absolute value of I r would be r only, and absolute value of 0 to pi f r I e I r times e to the power I theta e to the power I theta d theta. We would be using another inequality which is on the line integral, when we say is that absolute value of integral along a line f z d z is always less than or equal to integral along the line of f t, absolute value of f t dt. This is from the line integral we are getting. So, if I do use those results, I would get that this would be less than or equal to r 0 to pi integral of absolute value of f r e to the power I theta into e to the power I theta d theta. Again, this we could treat as two functions. So, absolute value of e to the power I theta I will treat as 1, and f r e to the power I theta, that we have just absolute value of this we had find out, this bounded by k upon r e to the power minus r sin theta. So, what we get is that this would be less than or equal to k upon r e to the power minus r sin theta. Since this k and r, they are constant, so I could take them out from the integral sign. So, r into k by r I would get it as k, and then the integral from 0 to pi e to the power minus r sin theta d theta. Now, here I can use this is now in the integral, which in the Jordan's inequality we are finding it out. So, I could use that Jordan's inequality, and I could write it as less than pi upon 2 r, that is this is less than k upon pi 2 r. So, now what I have obtained, the upper limit, or that the absolute value of this integral along the semicircle of the function f z. F z is now my the function, that actual function we have started, that z e to the power I z upon z square plus 2 z plus 2, that is bounded by k pi upon 2 r. Now, you see we have find it out. There we had find out, first one was k upon r. Now, you see is that was k pi. Now, we have find out k pi upon 2 r, a more finer upper value, and which is depending upon r, that says is as we take r larger and larger, it will approach to 0. Now, since this is a positive value, absolute value is positive value. So, if it is approaching to 0 as r is approaching to infinity, it says is that value itself must be 0. What it says is that the integral of f z integral of f z along this semicircle S must be 0. So, we had shown here that z e to the power I z upon z square plus 2 z plus 2, its integral on the semicircle S with respect to z is approaching to 0 as r is approaching to infinity. So, here we had used this one result, which is called as Jordan's inequality, or sometimes that result which we had proved the Jordan's inequality, that is also called Jordan's lemma. Now, if we use this one, that says is that now we have got the result as a. So, now what we have obtained, that integral along the semicircle S of the function z e to the power I z upon z square plus 2 z plus 2 plus the integral along the real line minus r to plus r x e to the power I x upon x square plus 2 x plus 2 dx. This is by the first result pi times minus 1 plus I into e to the power minus 1 plus I. Now, since r is now take the limit as r is approaching to infinity, then just now we had shown that this integral would approach to 0. So, and this integral would be actually the principal value of this one, or rather you could say this integral would approach to minus infinity to plus infinity x e to the power I x upon x square plus 2 x plus 2 dx. This would be this right hand side. Now, right hand side I am writing in expanded manner. It would be e to the power minus I minus 1. So, e to the power minus 1 I am writing as pi upon e. Then e to the power minus I we could write as cos 1 minus I sin 1. So, I would get minus 1 plus I into cos 1 minus I sin 1. Write this real and imaginary part separately after multiplication. It gave me sin 1 minus cos 1 plus I times cos 1 plus sin 1. Now, see the left hand side. Left hand side we do have this integral of x into e to the power I x upon x square plus 2 x plus 2. While I have to evaluate the integral of x into sin x upon x square plus 2 x plus 2. So, e to the power I x here also we could write as cos x plus I sin x. So, this left hand side also we can break it into two integrals as the real and imaginary part. Now, equate from both the sides the real and imaginary part. So, we want sin x would be coming in the imaginary part, that is from both the sides imaginary part we have to equate. So, from here the imaginary part would be integral minus infinity to plus infinity x sin x upon x square plus 2 x plus 2 dx, which would be equal to pi upon e times cos 1 plus sin 1. So, we had evaluated this integral, where of course, my function f x was not satisfying the degree condition. Let us see one more example of this kind. Evaluate this integral minus infinity to plus infinity x plus 1 cos x upon x square plus 4 x plus 4 dx. Now, you see here we are again having the integral of the form minus infinity to plus infinity f x cos s x dx, cos x dx. Now, the function f x here is your x plus 1 upon x square plus 4 x plus 4, that is it is a rational function having two functions p x upon q x. Both p x and q x are polynomials. P x is a polynomial of degree 1, q x is a polynomial of degree 2. Q x is not having any your real zeros. So, what we do get as a solution, we would start with, but the condition is that the degree condition is not being satisfied. So, we will just find out the corresponding complex function z plus this function is x square plus 4 x plus 5, otherwise it will have real zeros. So, if when it is 5 only, then it will not have real zeros. So, this question has to be x square plus 4 x plus 5 here. So, corresponding complex function we would write z plus 1 e to the power I z upon z square plus 4 z plus 5. Make this factors, it would be z plus 1 into e to the power I z upon z plus 2 plus I into z plus 2 minus I. The zeros of the denominator are minus 2 minus I minus 2 plus I, where minus 2 plus I would be in the upper half and minus 2 minus I would be in the lower half. So, we do have that this function is having only two simple poles at minus 2 plus I and minus 2 minus I. So, in the upper half plane there is only one simple pole. Let us use the residue theory over here. So, we will choose the contour as usual the semicircle which if I am choosing it of the semicircle of the size of the radius 3, that would include our minus 2 plus I. So, just one semicircle, and then from minus r to plus r, this real line, this closed contour we are taking. In this there is one simple pole in interior to this one. So, using the residue theory, we do know this integral along this closed contour would be 2 pi I times residue of the function f at the simple pole. So, first let us use this calculate this residue at this simple pole minus 2 plus I. Again, because it is a simple pole, I would use the first formula of this function residue at z is equal to minus 2 plus I into f z, as limit is z is approaching to minus 2 plus I, z plus 2 I minus I into f z. If I multiply z plus 2 minus I with this f z, I would get z plus 1 e to the power I z upon z plus 2 plus I. So, I would get limit z is approaching to minus 2 plus I of z plus 1 times e to the power I z upon z plus 2 plus I. To evaluate this limit, first we just have to write our value that z is equal to minus 2 plus I. So, from here what I would get it, z minus 2 is I. So, z plus 1 would be your 3 plus I. So, what we are getting is minus 1 plus I e to the power minus 2 I minus 1 upon 2 I, as usual. You just now using the residue theory along this closed contour C, this closed contour we are just now again breaking into two parts. One is the circular one and the another is this part of the real line. So, we are writing it as integral of z plus 1 e to the power I z upon z square plus 4 z plus 5 d z along the semicircle S of the radius r, plus the integral along this real line from minus r to plus r, and that we are writing in the x format. So, x plus 1 e to the power I x upon x square plus 4 x plus 5 dx. Now, this we have to now show that integral along this is 2 pi I into residue at z minus 2 minus 2 plus I z plus 1 of this residue of this function. This residue of this function just now we had calculated this one. So, if I multiply it with the 2 pi, 2 I and 2 I would cancel it out, I would get again minus pi into 1 plus I into e to the power minus 2 I plus 1. Now, the thing remaining is that is now we have to take the limit as r is approaching to infinity. So, and showing it that this has to go to 0, then this would going to the desired integral of minus infinity to plus infinity. So, let us try to show that the integral of the function f z, that is z plus 1 e to the power I z upon z square plus 4 z plus 5 along this semicircle S of the radius r is approaching to 0 as r is approaching to infinite. Let us go ahead with our usual method, find out the absolute value which is being this bound above of this function, what is the and then using this Emil inequality. So, again if we are going it in the usual manner, we are finding it out that we could write it as mod of z plus 1 into e to the power I z upon z square plus 4 z plus 5, which we could get it as should be less than or equal to mod of z plus 1 upon mod z minus square root of 5 whole square. This again we would be getting in the form from the inequality, that is that we would explain. Now, let us come over here. Mod z, if I am taking common from here, I would get 1 plus 1 upon mod z, and this we are writing is mod z plus 1 is less than or equal to mod z plus mod 1. So, and from here if we are taking common mod z, I would get mod z square and 1 minus square root 5 upon mod z whole square. Now, since mod z is greater than r, if I do take, I would get this is bounded by some constant, this is bounded by some constant, that is this is bounded by some constant, this is bounded by some constant, and here is since mod z is greater than r and we are getting is 1 upon mod z. So, this should be less than 1 upon r, and e to the power I z, if I treat it as 1, I would get the bound as k upon r. Again we have got the bound as k upon r for the function f z. So, if now I use the this ML inequality with this bound, what I would get, that would be again a constant. Now, let us see this explanation for getting this z square plus 4 z plus 5 as larger than mod z minus square root 5 whole square. This z square plus 4 z plus 5 with the factors z plus 2 plus I into z plus 2 minus I. Again writing it is greater than or equal to mod z plus minus mod of 2 plus I and mod z minus 2 minus I. The absolute value of 2 plus I is 4 plus 1, that is 5 square root of 5. Similarly, the absolute value of 2 minus I is also square root 5. So, this is simply mod z minus square root 5 whole square. This is the explanation for this denominator. Now, if I use this ML inequality over here, I would get the absolute value of the integral S, integral along this semicircle S of z plus 1 e to power I z upon z square plus 4 z plus 5 dz. Because the absolute value of this is bound is k upon r, this m, and L is the length of this semicircle, which is pi r. So, what we would be getting is less than or equal to k r into pi r. Oh, that is again a constant. So, now this constant bound is not depending upon r. So, this we cannot guarantee that this would approach to 0. So, again we have to use the method that e to the power I z, we would not take the absolute value, the bound for this as 1, rather we would try to write it out as e to the power minus r sin theta, and then the integral along that circle semicircle S we find out more finer bound. So, again we are taking this function z plus 1 e to the power I z, z square plus 4 z plus 5, this we had just shown that is less than or equal to mod z plus 1 into e to the power I z upon mod z minus square root 5 whole square. Now, e to the power I z on S we would be writing it as e to the power I r e to the power I theta, because the semicircle this S is r e to the power I theta in the parametric representation for the theta lying between 0 and pi. E to the power I theta, again in the similar manner we would be writing cos theta plus I sin theta. So, what we would be getting is absolute value of e to the power I r cos theta into e to the power minus r sin theta, this is 1. So, again we would be getting is e to the power minus r sin theta. In the similar manner, so this bound for f z, that is now I am writing as f r e to the power minus theta. This what we would be getting is, that is this part again as such is mod z, or rather you could say this, for this part we had already got that this is less than some constant k upon r, and e to the power I z is e to the power minus r sin theta. So, we would get it k upon r e to the power minus r sin theta. Now, we use this finer bound of this function f for writing this. This is true for all theta, because this Jordan's inequality is true for this 0 to theta lying between pi. So, we do find it out that this is on this whole path of integration, this bound is true. So, now we get S f z, we would be writing again in the form of this parametric representation. We could write this as 0 to pi f r e I to power theta into I r times e to the power I theta d theta. This now we would be using this absolute values. So, this just now, and this would be less than or equal to, or this we could say is I r integral 0 to pi f r e to the power I theta e to the power I theta d theta. Now, again we would be using for the line integral, that is line integral along a path of absolute value of the integral. This is always smaller than the integral of the absolute value of the function. So, absolute value of I r is r only, and this is less than 0 to pi integral along 0 to pi of the absolute value of f r e to the power I theta into e to the power I theta d theta. Now, absolute value of e to the power I theta is 1, and absolute that we will take as 1, and the bound for f of r e to the power I theta we would take as k upon r e to the power minus r sin theta. So, since this is less than or equal to, so the integral would also be less than or equal to r times integral 0 to pi k upon r e to the power minus r sin theta d theta, and this k upon r is a constant. So, that we would take out. So, we will get less than k times 0 to pi e to the power minus r sin theta d theta. Now, for this integral we would use, because this is from 0 to pi, we would use our Jordan's inequality, and that says is it is k times pi upon 2 r. Now, we have got for this integral the absolute value a finer bound as in the previous method, and this finer bound is depending upon r. So, as we are increasing r, this bound would be decreasing towards 0. If bound is decreasing towards 0, what it says that this integral must be 0 for that large r, or that we could say is that this integral s along this f z, this approaches to 0 as r is approaching to infinity. Now, so what we have got is, we have got that integral along this s z plus 1 e power I z upon z square plus 4 z plus 5, and integral along this real line minus r to plus r x plus 1 e power I x upon x square plus 4 x plus 5 dx. This we had already obtained is equal to pi times minus 1 plus I e to the power minus 2 I plus 1. Now, take the limit as r approaches to infinity. Then the second integral would be, actually we could write as integral minus infinity to plus infinity x plus 1 e to the power I x upon x square plus 4 x plus 5 dx, and this integral would be approaching to 0, just now we had shown, as r is approaching to infinity. So, this would be equal to this part. Now, this part I am writing is real and imaginary part separately as in the previous one. So, e to the power minus 1, that I am writing as pi upon e to the power minus 2 I, that we could write as cos 2 minus sin 2. So, we are having minus 1 plus I into cos 2 minus sin I sin 2, multiply it and write the real and imaginary parts separately, we get sin 2 minus cos 2 plus I cos 2 plus sin 2. Now, here the left hand side e to the power I x, again we can use in the Euler's formula, and we can write it as cos x plus I sin x. That says is this left hand side I have got actually two improper integrals. One is integral 0 to infinity x plus 1 upon x square plus 4 x plus 5 cos x dx, plus I times minus infinity to plus infinity x plus 1 times sin x upon x square plus 4 x plus 5 dx. Now, the integral which we have to evaluate, that was integral of minus infinity plus infinity of x plus 1 cos x upon x square plus 4 x plus 5 dx. Now, this is the real part of this integral. So, we will equate it with the real part says is pi upon e sin 2 minus cos 2. If I have to find out the imaginary, that is if it would have been sin x, I would have used this imaginary part. So, thus today what we have learned, that even if our function f is not satisfying the degree condition, there is one more term or one more method we had learned, or one more result we had learned, that is called the Jordan's lemma, which said is integral 0 to pi e to the power minus r sin theta d theta is bounded by pi upon 2 r, and that result has helped us to evaluate some more integral of the form minus infinity to plus infinity f x cos x or f x sin x dx. Now, you see all these proofs when we were doing, we had find it out that in the examples we will find out that is first we used to take the degree condition, that the difference between the numerator and denominator degree must be at least 2. So, that the convergence condition or that integral along the semicircle of the function should approach to 0 as r is approaching to infinity. When we had find out the difference is only 1, we were reaching towards a k, that says is we are not actually able to find out that how it is reaching to 0, or how it should say is that it is equated to 0. So, that we could use the residue theory directly. Then we had used this Jordan's inequality and find it out that still if the function is of the form f z e to the power I z kind of thing, we could still write it out in the form of on the semicircle we could write it out as r into e to the power I theta, and from there we had got the clue, that is we could use this Jordan's inequality, and again we could show that the integral along this path, that is the semicircle as r is approaching to infinity is getting to 0, and then again we could use this residue theorem or residue theory. So, the examples we have done only one simple pole. If we do have more than one simple pole, certainly we can use the residue theorem, and then it would be 2 pi I times summation of residues at all those simple poles of the function f z. All these poles what we have taken, they were in upper half plane, and we had we have taken that my f has to be rational function, so that we could show integral along this semicircle approaches to 0. So, we have got that is either it is greater than 2, or we had reached that if it is greater than or equal to 1, still it is happening. So, we are not talking about the constant functions. Now, if my poles are, or if the singularity of the function is on the real line, all the times we have put this condition that q x should not have a real 0, that is we should not have the function to be singular on the real line. Now, if the function is singular on the real line, what will happen? That we would see in the next lecture, that is if this condition that q x has no real 0, if this has been failed, still can we do apply this residue theory? The answer we would get in the next lecture class. So, today we had got that we can solve the functions, find out the integral of the functions of the form f x cos x or f x sin s x form of the integrals from minus into plus infinity, where the f x are failing with the degree condition on the numerator and denominator of greater than 2, or let us see, that is we have got the results that when these kind of integrals are being evaluated, we can use the degree condition that it is greater than or equal to 1. So, that is all for today's lecture. Thank you.